all. This is Mr. Yeager for chemistry. I'm looking at isotopes this time. So we talked about the atomic structure that has protons, neutrons, and electrons. And one of the main things from the last video is about how protons with the atomic number tells you exactly what element you have. And so that every atom of a particular element have the same number of protons, but they could still be different based on the number of neutrons. So we call them isotopes. And so that's where you can see the definition there. Isotopes have the same number of protons, but different number of neutrons, so different mass numbers, okay? So jumping right into this, one of the things we like to do with this is give you a couple different isotopes of an element, and for you to figure out the protons, neutrons, and electrons. And all we should see that changes is the number of neutrons. So looking at these three isotopes, I have hydrogen 1, hydrogen 2, and hydrogen 3. That's how we would say it. All right. If we recall, this number after the element is the mass number. Okay, so it's not the number of protons, it's not the number of neutrons, it's not the number of electrons, it's the number of protons plus neutrons. And so how I'd figure this out is I'd look up hydrogen on the periodic table and see that it has that number 1 at the top of the element. And that means that that's the atomic number, so all the hydrogens have 1 proton. We can then skip neutrons for a minute. We can say all the hydrogens have 1 electron because we're still assuming they're electrically neutral. Then what I have is I can figure out the number of neutrons by simply subtracting the mass number from the protons, or just thinking about it kind of logically and going 1 plus what is 1? 0. And I know that I'll start with saying something there real fast is the fact that some people are like, wait, 0 neutrons? Yes, the hydrogen atom, actually the most common one, is just a proton and electron. Now hydrogen 2, it would be 1 plus 1 equals 2, so that one does have a neutron, and then 1 plus 2 is 3, so that one has 2 neutrons. So all those hydrogens have the same number of protons, but different number of neutrons. If I try out magnesium over here, magnesium has an atomic number of 12. So all of them have 12 protons. All of them have 12 electrons. And then I have to subtract from the mass number. 24 minus 12 is 12. 25 minus 12 is 13. 26 minus 12 is 14. It is very common that you'll see that there are just usually 1 or 2 more neutrons in the isotopes. There are some rare elements out there where it could jump 3 or 4 neutrons between the isotopes. But generally with the smaller ones, they're usually just 1 or 2 neutrons larger. All right, so that's kind of the first big thing to kind of do with it. The other thing that really comes out of isotopes is understanding where this atomic mass number comes from, okay? And again, because this number is fairly useless to us at this point. It does not help us figure out protons, neutrons, and electrons, all right? But where do we get that phosphorus is 30.974 AMUs? Like, there's no such thing as a 0.974 proton, okay? You can't do half of a proton. You either have one proton, a full proton, a full neutron, or whatever. So this comes from the averaging of all of the different isotopes that are present for phosphorus, okay? And this is another name for it. We call it the relative atomic mass. A lot of times we ignore the term relative, but for this we do say it because the idea of relative is it's telling you it's an average of all the different isotopes, and it's a weighted average. You know what weighted averages probably are. They are things where just a lot of schools do it with their grades, where their test grades are weighted 75% of their grade, while their formatives are weighted 25% of their grade, or something similar to that. All right, that's what we're doing here. So this 30.974 is basically trying to say, like, what isotope is the most abundant versus another one that might not be abundant, but is pulling that average up or down. Okay, so it is an average of all of those. Now at the bottom here, the units for this is the atomic mass unit, AMU. One of the few times we really do use it. Okay, so if I have to calculate out relative atomic mass, it's basically just a big repetitive calculation. You do the mass number of isotope 1 times its percent abundance, mass number of isotope 2 times its relative abundance, plus ... So if there's a third isotope, fourth isotope, fifth isotope, you keep going. Okay. You need to make sure to change those percent abundances to decimals before you calculate it. So move that decimal point 2 spots. Okay. And then a couple of hints. The RAM, the final answer you get, must be between the smallest and largest mass. This is one of those things where I find it silly when people make this mistake. You're still taking an average. And so if you're averaging like the hydrogens, 1, 2, and 3, you clearly have to know if you get an answer of 5 or 6, that's impossible. You probably didn't move a decimal point correctly. So the RAM has to be between the smallest and largest mass. And then another hint is the RAM will usually be closest to the most abundant isotope mass number. Okay? And so we use this to help make predictions of what might be the most abundant isotope. Going back to what does percent abundance mean, what I mean by that is if I grab a ton of hydrogen atoms, a certain percentage of them should be this isotope number, a certain percentage should be another, and then so forth. So it's like basically taking a bunch of M&Ms and going how many of the M&Ms are red, how many are orange, how many are blue, etc. in a particular bag. So to kind of illustrate this before we do a calculation, going back to like hydrogen, the 3 isotopes of hydrogen, hydrogen 1, hydrogen 2, hydrogen 3. On the periodic table, the relative atomic mass for hydrogen is 1.008. So based on seeing that, hopefully you guys can figure out and go, which of these is probably the most abundant? Well, H1. And it is. Like 97% of all hydrogen atoms are hydrogen 1. About 2% are hydrogen 2, and about 1% will be hydrogen 3. Okay? So that's why that number is so skewed toward 1. Really close, showing you that that's going to be the atomic mass. Same thing goes with phosphorus. All right? Phosphorus had an atomic mass of 30.97. All right? I don't know off the top of my head what are the different phosphorus isotopes, but if I said make a prediction of what do you think is the most abundant, if you said P31, perfect. Now, is that the right answer? I'm not completely sure. We'd have to go check. It's possible that phosphorus has isotopes that are 28, 30, maybe there's not even a P31, and there's 33 and 35, and 28 and 30 are pulling that average down toward it a little bit closer, okay? But it's a perfectly good guess to be like, I think P31 might be the most abundant isotope. Again, who knows, okay? Until you look it up. So let's go and do a calculation. What is the relative atomic mass for chlorine? If you know that chlorine 35 is 76% abundant and chlorine 37 is 24% abundant. So if we do this calculation, 35 times 0.76 plus 37 times 0.24. So you can see mass number times relative abundance. I can do those two calculations separately. It comes out to 26.6 plus 8.88. And my relative atomic mass is 35.48. So it's a very repetitive calculation. The only mistakes I see people run into is they don't move the decimal point correctly, or they switch the percentages and the numbers and just make a mess of it. Okay? So just be careful. All right? Now I want to show one other thing. Okay. What if I had a question where it makes you solve for maybe one of the other isotopes numbers, where they give you the RAM? Okay? How do I do this calculation? Well, we still set up the formula the same. Okay? It's still RAM equals isotope 1 times abundance plus isotope 2 times abundance. So what I would do here is I'm given the RAM, so 24.65 equals isotope 1, 24 times times 0.7 plus x times 0.3. And it's just an algebra equation. Okay? If I solve this one for you, I would subtract out the 24.7. 24 times 0.7, so that would be 24.65 minus 24 times 0.7. That comes out to 7.85 equals x times 0.3. I divide both sides by 0.3. And this comes out to, yeah, you'll get kind of a funky decimal. It's 26.17. I mean, you could basically say maybe like that can be rounded down to 26, okay, because it does have to be a mass number. So again, that's the part where these problems would be set up very, very clearly with very specific percentages so that you clearly see what the other mass number should be. So the other element is x26, okay? Again, I'm making this completely up, but I'm just trying to show that you could still solve for something inside the parentheses as well, so don't be too worried about that. Okay, that's about all. Thank you.